Hello, console room. Welcome to Sunday. It is time for us to welcome Jeff Thole to the stage.
I get that every time I start a classroom. All right, hopefully you can hear me. Does that sound okay? So, my name is Jeff Thole. I'm the laboratory supervisor at McAllister College. And Don was there pointing these examples to us not too long ago, talking to some of my colleagues, and I happened to be in the wrong place at the right time and agreed to do this. So I'm going to basically show off some of the tools that we use as geologists to do some investigations. So a little history. I grew up in Minnesota. I went to Minnesota State for 1 year. I wanted to get away from home. I then transferred out to UNE, University of Minnesota Duluth. The geology program there was well known at the time, and it still is. I think I saw my folks more when I lived in Bemidji 3 hours away than 20 minutes, but it was enough separation. And anyway, I got a degree. I went an extra year, loved school. I got a position with the USGS in Western Virginia. That's the following summer after I graduated in '87. And it was a 3-month position that they extended. And I could have stayed any longer, but I knew I wanted to go to graduate school. So I drove from Western Virginia up through Niagara Falls, around Lake Superior, stopped at home, and then off to Washington State and home in Washington. Following that, I came back to Minnesota. I had somewhat of an intent to do a PhD. I wanted to go to New Zealand and work on some volcanoes in North Island. But life happened, and I ended up getting a job with an environmental consulting firm. And I actually worked for 2 different consulting firms for about 5 years. And as one was wanting to do back in the day, we would, to jump the salary ladder, you would look for different jobs. We didn't have the internet, and so we had to start the internet. I was looking through, and there was a job listed for laboratory supervisor at McAllister College. And they had certain equipment that I had used in grad school, and it was like the job description was written for me. I was lucky enough to get that. So in October of '96, I came to McAllister College and had a look back. And some of the nice things we get to do is travel. And I've been to some amazing places. I've been to Baja a couple of times with my colleague. Spectrox-opy Island we did some work on. Spectacular location, quite remote. Been to Iceland a couple of times with my colleagues from St. Thomas, their program. I helped to teach a field course there. Spectacular, I want to go back. Bahamas, I've been to San Salvador. We brought classes down there on a number of different occasions. To the X-rays Research Center on San Salvador Island. That also pretty remote, but spectacular location and great fodder for student projects. We've taken first-year courses to Oregon and Northern California. So my colleague Alan Chapman got this career grant when he started, and it allows us to bring a class of 16 students for part of their first-year experience. Amazing. And a lot of you probably know my colleagues Ray Rogers and Kristen Rogers, who've given me presentations here. And I spend a lot of time. I've been fortunate they've kind of taken me under their wing. And I tag along, and we go to Ray and Kristen's research area in central Montana. And we'll do 3 to 5 day floats sometimes on the Missouri River. And last year they found a beautiful specimen of the Bureau of Land Management found it, but they found a few isolated vertebrae. Ray and Christy went out there and identified it as a disease disorder. And I've talked to Don about this. We had a new mascot that was selected, and it happens to be a Highland cow. We wanted it all to be Loch Ness, which in essence is a disease disorder. It would have played in beautifully to the story if that would have been chosen. So we go out there quite frequently. This was the picture here of the Thole was a gateway program to the Geology Consortium. And it was an introduction for younger students to be involved in research and expose them early and hopefully increase diversity within the program. And probably my favorite way to go look around is to take my kids and we would drive to Las Cruces, New Mexico, where my folks would be living, and so my son, Charlie's here. I don't think he's seen again. He's not. And then my daughter, this shows you how much of a geology geek I am, but her name is Emerald. And so Emerald Bay, which is the place actually in Lake Tahoe where my ex-wife and I got married in 1992. But we've done some great travels and seen some great things from that, from geology specifically, but also through family. So here's some of the tools that we have that I was just telling John that I don't want to retire because I don't want to lose access to these things. And I use them all the time for lots and lots of different things, actually. And what I thought I'd go through is describe how we use them, how they operate to some extent, and then we're going to give a specific example, and we're going to connect to one of these instruments at the end to help answer a question. So the unifying theme here is X-rays, and I use the term Spectrox-opy. I didn't know anything about doctoring, and a little bit here and there, since late episodes, but my son Charlie filled in and said, oh, Spectrox is this thing they mined in some of the most famous episodes of future years. So I tied that into the title. Two of the instruments that we're using have spectrometers, and one of them uses X-rays. So that's my mistake for including that, but it's one of the most useful that we actually have. So what is spectroscopy? It's simply the study of part of the electromagnetic spectrum. Visible light between 400 and 700 nanometers roughly. We're all hopefully familiar with that. But X-rays are a shorter wavelength and incredibly useful tool. They can be dangerous, but they're also incredibly useful in a lot of different ways. Most of you have probably had medical X-rays before. Gamma rays are shorter, and one thing I didn't show, we do have a gamma ray spectrometer that we use periodically for some different things. We detected, we melted some snow, and we detected fallout from the Fukushima disaster back in the day. That was quite interesting. So, micro-XRF. This was the device that we got in 2017. We were lucky enough to get a specific grant, and we purchased this. We actually got a used version of this based on the amount of funding we had. We couldn't afford a new one at the time. And we got a demo unit from one of the labs in Berlin, so that's where they're based. But it's an X-ray spectrometer. So we're using X-rays to produce X-rays, and we're recording the position of that. So the real money in this machine is actually the stage. The reproducibility of the stage on a micron level is kind of astounding. It's also great because it's non-destructive. We can throw anything in there, we don't have to coat it, we don't have to crush it. It's helpful to have a polished surface to get the best data, but it can be non-destructive. We can actually do liquids in there too if we leave the vacuum off. But this tool we use in many classes. It's easy to use, get some interesting data. We always, regardless of the sample, we usually see something interesting that we didn't expect, which is cool. So there's an example. Most of you probably heard about manganese nodules that they're looking to start mining the ocean basins before we know anything about those ecosystems, and it's a little scary. They call them polymetallic nodules for a reason, and a lot of different elements that are present within those. So what we're seeing is the spectrum in there is what we call an energy dispersive X-ray spectrum. The X-ray detector that is in there detects all of these at any one time, That's a sum spectrum. So that's X-ray data from across the whole of that sample. We can actually select little portions of that, which is quite useful as well. And then we assign a color. So the colors obviously are not real. We try to come up with some aesthetic combinations. But here we choose to display calcium, titanium, and nickel. What's kind of interesting too in this particular specimen, the nodule is probably a couple inches across. A friend of mine brought it in, we cut it and polished it. He let me keep half of it. The layering that you see is quite interesting. In fact, this one has a core, a green core. It's, in essence, it broke off a pre-existing one and then it started the process over again. That was completely unexpected. The spectrum in it, which I didn't, you probably, I don't think you can see it very well. I'm guessing you can't see the labels, but each of those peaks represent a specific X-ray, specific X-ray energy, which represents a specific electronic transfer of electrons in the nucleus of a specific type of atom. I see calcium, potassium, manganese, obviously, iron, cobalt isn't labeled, but that's in there, zinc, copper. So these are going to be a tremendous source if we can figure out ways to harvest them safely. I'm going to show you, here's the inside of the instrument, and I've got a little video that's just a very short clip that gives you an idea of how the sample goes underneath under the X-ray beam. So there, we're just moving back to start the scan over again, but it's taking steps in the Y direction, if you will, at a distance that I specify. And in a single sample, there can be over 1,000 lines in something that's only just a couple inches across. I'll just do a little more time. I have the rate on this particular scan was set to, that's jumping back, but then it moves at 600 microns a second. So it actually takes some time. So we can display multiple elements from the specific scanner, we can display individual elements. And some of them are pretty spectacular. It's the same gentleman that gave me the manganese nodule had what's called an ironstone accretion that he had given it as a gift to his grandkids. And here I'm displaying silica, calcium, and an iron. And some of you might recognize this is what looks to be very similar to what we call a septarian nodule. And those are usually mudstone with a pattern like this on the interior that's predominantly just calcite. And here we have mostly calcite surrounded by iron, but interestingly, the silica there, the blue color is actually quartz. We don't often see that in not the polymetallic nodules, but the septarian nodules. Another good example here, there was a donor, this wonderful woman who donated a whole collection of agates and other things that were collected in the 30s by her husband when he was a child and her father-in-law. And this particular agate, I think, was collected in 1996 in Scandal, Minnesota, which is about 3 miles from where I grew up in Esco. What's cool about this one, I mean, it's a couple of inches across, and the reddish color that we see in spare agates, we know comes from iron, and it's usually in specific layers. And sometimes the agates, they can be spectacular, they might have enough iron to detect, they might not. This one actually has copper, and copper in the layers that are opposite from where we see concentrations of the iron. So there's something interesting going on there. If I did it over again, in schooling, I would spend a lot more time on redox chemistry, because I think that's a big part of the answer to the formation of agates. We still don't have a real good model for how these are formed. We know where they're formed, we know they're formed in different environments, but we don't have a real good model. Nobody's ever synthesized an agate. If you can do that, you can be incredibly wealthy. Because they're going to run out. It's a finite source. At the Geology panel, Geology Presentation, Don passed around a slab of the diverse shale, which is actually these inter layers that are mostly calcite. These limestones that are full of fossils. And this is an example. And it's just simply displaying manganese and iron in this particular case. And you can see there's brachiopods, there's crinoids, there's rhizomes, trilobites, maybe actually see in there. And it might be an interesting tool. I think we can almost quantitatively map out, because some of the brachiopods in this are showing some manganese and iron, some are not, which I find kind of fascinating. We had a student that brought back, I don't know how many pounds. They went down to the end of the summit, as a mile or so from school, and was seeing these pieces, and brought back tons and tons of them. And he turned it into his senior honors thesis, and what we were finding interesting was things that were containing abundance of phosphate, which is in bone. There wasn't a lot of vertebrates at the time, 450 million years ago. There was early fishes that we know about, and we were seeing these flashes of phosphorus. We weren't exactly sure where they were from, and our student was, we started calling them fish pits, and it's like we can't put the cart before the horse. We got to figure out what this is first. Turns out they were phosphatic rhizomes, which normally they're calcite, and that was an interesting result. It wasn't as exciting as finding a new fish species, but we always see something interesting with this, and it's a great teaching tool. So we have this. The next device, which is a spectrometer, this is the X-ray spectrometer that we have. And we've had this since 2005. Our service contract ran out. We had to start thinking about replacing it. This was $147,000 back in the day. The micro-XRF was $130,000. This particular instrument was funded by a National Science Foundation grant to one of my colleagues. We're probably going to have to write another one to replace this, but it still runs. What we use here is we use X-rays to bombard a sample, and we look at the results of that, and we get diffraction if it's a crystal material. I'll explain that in a little bit. But it gives us a structural data. It's not chemistry, it's structure. So to have this and the micro-XRF and the ESM are complementary. Sometimes we need basically all three to figure out specific questions. It's a destructive technique. We have to make a powder, which can be problematic in certain cases if the sample is precious. But I'll show you an example of what we actually put in there. Here again, I have another a little video of a little robot arm. There's a sample changer. And then we'll grab a sample, move it to the analytical location, and what you're seeing there was the detector moving down. It actually has to move up out of the way to get the sample in. And then this little light comes on, there's a click, and that's letting the copper X-rays out that are bombarding the sample at a specific angle. And we will scan through a range of what we call 2 theta. And see what the results are that we get. So, kind of cool. The nice thing too about that is students can reach into or place it right there and not have to reach into the business side of things. I always tease them when we run this because it's locked. You're not going to get exposed to X-rays to that. I'll put my hand on the outside of it and like, oh, it's getting warm. And it's not doing that, but they don't know that. So on the left there's a little 2-inch circle with what we call a zero background plate. I've powdered a little bit of the sample, and we use an agate mortar and pestle in some cases, and then that is what we have to put in an instrument. The results then are this is what we call the fractogram, and each of those peaks are a solution of what we call the Bragg equation. And the sum total of those peaks and the intensity of those should be unique to a specific structure. The more mineral phases that we have, the more complicated it actually gets. And so ideally, if you can separate things out, it's better. But it's structure, it's not chemistry. So The Bragg's father-son team figured this out in the early 1900s, in fact, in 1912. They won the Nobel Prize in 1915. The youngest science recipient of the Nobel to this day was the younger Bragg, and the only father-son team to ever get it. And it's a fundamental relationship that they figured out back before fancy electronics. It astounds me sometimes thinking about how these guys learned as much as they did with the equipment that they had at the time. And so the n lambda equals 2d sine theta is this fundamental equation that we use in other technologies as well. And lambda is the wavelength we're using copper scale for radiation. We know the wavelength of that. 2 times d is the interplanar spacing. And then sine theta is the angle that we're actually scanning at. And d is the interplanar spacing of crystalline substance. So if we don't have a crystalline substance classes, we don't get a diffraction peak. So the reason we grind a sample is that we can have every possible orientation to allow us to potentially diffract each and every one of those planes that then will be unique to that particular substance. So it's quite useful, but a lot of times we have structures that are the same, and we need the chemistry then to actually figure that out. So it's often you get an answer. Sometimes it's not satisfying, and that's actually what we're going to follow up with. So, as an interesting aside, you probably heard the adage, the best geologist has seen the most rocks. I kind of believe that. And what we see there, the lower corner there, is a volcanic rock that was brought to us by an alum that he's a biologist, but he traveled to Indonesia. There's a place called Bluestone Beach. And he brought us back, and nobody could tell him what the blue, kind of bluish-green teal color was. Well, we got it, polished it, and I finally ran it after quite some time. I don't have an answer yet. Well, this project that we do in our introductory class, a student bring a rock, in the one on top, that layered one, which doesn't look like it's related genetically. One's a volcanic, lava flow or potentially acidic. The other one's a sedimentary rock. But I looked at that and I asked the students, does this happen to be from Indonesia? And they're like, yeah. It's from the same island. It's from Flores Island in Indonesia. So I've since X-rayed both of them, and what we've come up with so far is it's got quartz in it, which we expected. It's also got a zeolite mineral, which is an alteration product of volcanic rocks often, and it's a mineral called bornite. It's in both of them. So these probably came from the same volcano. I still don't know yet what the bluish greenish color is, but I'm getting close. And we're going to probably use the next tool to help us answer that question. But that was astounding to me that I can look at a rock and just based on color know that it's from halfway across the planet. Not always the case. So diffraction we use fairly frequently, and it's one of the tools in our arsenal of actually figuring out, basically what minerals are present in a sample. So the most fun sample, piece of equipment that we have is the scanning electron microscope. We've got this through another NSF grant in 2010. $351,000 for this one. And it includes 2 X-ray detectors. You can see one off the left side of it. The big planar white thing is a wavelength spectrometer. And then 2 different computers. It's an expensive piece of equipment. But here we're using electrons to produce X-rays. So we're producing images with a couple of different types of detectors, and we can also get chemistry data from that if the conditions are set up correctly. So we can display that like the micro-X-graph. We can do area maps, but it takes a long time. But we can pick points and pick specific, very small features and actually get the chemistry for that. The magnification goes close to 300,000, but we can't get things in focus at 300,000. And basically, we're on the first floor, which is effectively the third floor because there's 2 layers below us. But the vibrations within the building would preclude us from getting lower, resolution. We can still see things that are a few nanometers across. But the stuff where you see atomic scale things that they can do today, which is astounding. The University of Minnesota has some of these transmission electron microscopes that are a couple $1 million. Those are separate from the building. So they actually will pour a concrete base, set the instrument on that, separate it from the building. You have to step on the instrument to load it, and then you step off it to run it. That's not the case for this. And the scales of things that we look at are generally millimeter to micron scale things. So it works for us. This one is going to go off service contract soon. We're going to have to think about replacing this at some point too. So we use a tungsten filament in this particular instrument, and that's, if you can see the little blue, I don't know if you can see the mouse, this column, the cartoon here is a blow-up of the column. We have a tungsten filament in there which we heat up to a few thousand degrees Fahrenheit. We draw the electrons off. I mean, the filament is exactly like an incandescent bulb. It's a piece of tungsten. Those electrons get focused down the column. Since they're electrons, we can't use lenses, but that in this case happen to be magnets. And we're going to take and we're going to raster the beam across the sample. So it goes through a few different focusing magnets. It goes through an objective lens aperture, which is a little 30 micron hole in a piece of molybdenum. And then we raster the beam over the sample. And then all hell breaks loose. All of these different things are happening at once. And we get visible light. We do have a cathodoluminescence detector, which we use we look at zircons, for example, and see are they complicated or are they one uniform color. And that's important for geochronology and dating. But we use secondary electrons to look at the topography. And we use backscatter electrons to look at what we call atomic mass contrast and see different minerals based on brightness. And then we produce X-rays. And so we use a different computer to do that, to run the X-rays, and I'll show you that in a little bit. So here's a picture of the chamber. This is the sample that's in there right now. This is a specialized holder that we had, JEOL. Is this company, Japanese Electronics Limited, wonderful company, wonderful machine, and the service is we have like 300 service guys available to us, which is quite nice. But they built this holder for us, not knowing that we were getting the wavelengths versus spectrometer. There's one of the positions we can't use. I know you can't see the real well from that, but we can put 3 thin sections and 3 round holders in there that usually hold standards. And right now we have a thin section in there, and then there's a little round stud that doesn't typically go on this holder, but I put it in there because I know the position that I can stop it at. I have ruined the backscatter detector, which sits right at the base of what we call the Thole piece. We've got students do that, and it's a $6,700 mistake the last time it happened. In fact, I was sitting at the computer with a student who I thought was interpreting the image just the same way I was, because we were watching as we raised the stage. It has to be about 10 millimeters, a centimeter away, and they ran the sample right into it. While I was sitting there, but we're fortunate we have a reasonable budget here. We were able to replace that pretty quickly. And then within a few days, they had one in stock, thankfully. But expensive mistake. So the chamber door gets closed, we pump it down, and then we turn on the beam. And so the best pictures you see from scanning through microscopes typically are things like bugs, pollen, things with a lot of topography. And in 2014, the one trip we went to the Bahamas, there was particular students that were just getting mauled by these neutrinos. And I said, if we can get one, let's bring it back. Well, we managed to bring one back. That neutrino totally it's across is about 2 millimeters. And the picture on the left shows one that's kind of desiccated. You probably can't see the detail, but like the eyeballs have collapsed, the thing has actually shrunk down because of all the fluids that were removed. But you can see the proboscis here. There's these 2 little tubes that are used to inject the victim with an anticoagulant. And then they basically slither up the soup. So in the end, this right there, that's about 5 microns across. That's what they use to slice you. And then inject you with the stuff that you get some students that were just completely covered in ice. Because it was so hot at night, they wouldn't cover up. The simple way around, bug stuff didn't work very well. But if you wore pants, you were fine. But that's kind of amazing, that level of detail that we see on this functional organism that is less than a couple of millimeters across. So that picture on the right is magnified about 4,300 times. And the scale bar, you probably can't read that, but that's a tenth of a micron. Actually, no, that's 5 microns on the right side. Another image that I loved was a dead butterfly that was found in my folks' cabin. Brought it back, just you could see the hair on the eyeballs, which was just really cool. Maybe they had compound eyes. And zooming on that, you could see the nature of the individual lenses. And then you can even zoom farther and see structure within each individual lens within that. So the little dots were interesting to me. I had seen that and expected. And if you look carefully, it was a fungus that was growing that was actually degrading this particular dead butterfly. That was a surprise. But again, you never know what you're actually going to see. I've worked with a lot of different scientists using this instrument, and on the left is an image of Hugh from Holland. So there's a geologist that I know that worked for one of the companies that I worked for back in the day. He's now working for the NR, but he's a geologist by training, and he's probably one of the world's foremost authorities on kiwi fruit. And we've published a paper. He's given talks at conferences in New Zealand. This is interesting work. We were measuring the pollen to determine the size to see if there was any relationship to the clothing level. Genetic stuff that I wasn't well versed on. The picture on the right was pollen from flowers from my yard. And my daughter and I collected these images, and well, she did most of the work actually. She did some astounding stuff as a student in junior high. And she was combining different imaging modes into an image that had a lot more detail than we normally see. And had just Photoshop magic to it, and then of course she figured out a way to colorize it. This was part of the microscopy exhibit that we did in 2012 in the science division that I had set up. We actually have pictures hanging in a local coffee shop next to campus. That was a fun project. Another cool thing that I could mention there, the biologist that's in our biology department, Circle Ware, his name, takes students to New Zealand and Australia at times. She collects these microharvestmen, which are little 2 millimeter organisms that are related to dandelions, and they describe them, they use the ACM, and they named 6 new species. This was quite, I forget when this paper came out, but they named one after me. I have a species named after me. Thole. So my son's pointing out that my colleagues like to point out that one of the unique features on this particular thing, this species, is the fact that it has a unique anal plate. It isn't just that. But kind of cool. I don't know too many people that actually have a species named after him. Rogers has a turtle from Madagascar named after him. Christy, I think it'll just be a matter of time before she has something named after her. But the best images that we see for this typically are things with a lot of topography. And it's a wonderful instrument for that. Another thing I didn't mention, that we're really fortunate to have this lab, we call it the Tech Lab. They put up some money quite a few years ago. students have access to this. So if you're in R1, University of Wisconsin, University of Minnesota, they have all this instrumentation and more, but undergraduate students are not going to be able to get to use it unless it's a really unique situation. Here, I can have them collect data in about 30 minutes. So some take advantage of it, some don't, but I encourage them. They have access to this stuff, which is quite unique. So moving on, I got to keep an eye on the time here. The other type of imaging that we use on here is which are backscattered electrons. What I didn't mention, secondary electrons are surface electrons that get kicked out by the high energy electron beam, and it's the quantity of electrons that make it to the detector. Well, if there's topography, things that are on a side point away from the detector will not produce enough, as many electrons as they make it. And so we see those differences in this grayscale. What we have to remember, it's not a picture, it's actually a signal. So it's the sum total of signal that we're measuring across the sample. So with backscatter electrons, those are incident electrons that have much more energy. They bounce around and they come back out with a lot of most of the energy they went in with. And the quantity of electrons there that make it to the detector that relate to the brightness is a function of the density of the average atomic mass. So the brighter something is, the heavier it is. In that picture on the left, I should have left these full size. We see differences in brightness. Those are different minerals that have different densities. And the brightest things are typically going to be things like iron oxide. It could be minerals with hair elements in them, like rare earth elements. There's a mineral called monazite that is quite bright. Zircons tend to be quite bright. And it's the little bright ones that are often the squirrel. Let's go check that out. And we get sidetracked pretty easy. Speaking of small things, the one on the right is a micrometeorite. So I've been working with a guy named Scott Peterson, who collects micrometeorites and has probably the largest collection on the planet. And these things are, a few tens of microns. And this is something that it takes a lot of work to find these things. He'll take magnets up on the top of buildings and collect sediments and then painstakingly go through those sediments and find features like this. So probably the most useful feature, though, on the SEM is the fact that we can get chemistry data from a very small location. And the thing on the left is that thin section of granite that we picked one of the spots in there, and we see the spectrum again, and we can see the elements that are present, and we can see the intensities which are related to the concentration, and then that pattern, doesn't tell us what mineral it is. We have to figure that out. And in fact, when we see oxygen, potassium, aluminum, and silica in roughly those ratios, we know that that's probably potassium feldspar. And then the micrometeorite is actually this band or bar olivine, and that has a unique structure, but the composition there is relative to olivine that's formed in space. That's probably 4.5 million years. So the chemistry is fundamental for us to be able to figure things out. We don't always know. Sometimes we need the expert to help us actually complete that picture, or vice versa. So that's in a nutshell, quick, how these instruments work, how we might apply them, and we've been using our introductory classes to introduce the students to the equipment that's in the lab. And the first thing that we typically go to, because it's the easiest, is the microsgraph. And so students will collect, we want to filter here on, this is our class, the dynamic earth change, which is basically, if any of you have taken neuroscience in the past, is the equivalent of physical geology. And we tell them about the project ahead of time to collect some samples, and then we bring back and we'll analyze them. And usually we start with the micrograph. Often that's enough, and students will base their whole story on just results from the micrograph. Well, one of the students on this trip in particular, we get great students. We're really fortunate. I'm amazed at the job that admissions does. We get smart kids. It's an expensive place. But none of them are smart kids. They're good humans. And we stay friends with a lot of these I know students from the first couple of years that I started teaching me. I don't say that it is just because my kids were there, but they both went to McAllister too, which is fortunate. So one of the students there grabbed a sample, and she didn't grab it on this trip. She grabbed it back in Colorado. She lived in Golden, and there's a place called Table Mountain. And she brought 3 different samples, and I said, let's run them all. And so we did it. And one of them in particular, if you guys have been to the North Shore of Minnesota, a lot of the volcanic rocks that are there contain secondary minerals in the void space. We call those amygdals. Agates are one of them, Thompsonite is another one. We see very specific zeolite minerals up there. This was different. In fact, I knew what it was, but I knew it was different than we typically see. And those white circles that you see there are void space vesicles, gas bubbles that have filled into secondary minerals. Well, this particular student not only did all 3 rocks, but she wanted to know, okay, let's figure out what that amygdal filling is. What is the mineral? From the microxrf doesn't quite have the resolution that the ASM does. It's a really good tool, but it doesn't answer the question for us necessarily. We knew what elements to expect. So we took a sample, we plumbed out, we kind of picked out a couple of small crystals, we crushed them, and then we ran them in the XRD. And so the XRD gave us 2 possible options. In fact, there were more that we could put in there. And it's a zeolite mineral called chabazite. And we don't see that in great frequency on the North Shore. But we wanted to know which one. And we couldn't tell from the microxrf, so we then took the sample and crushed, well, actually, we took a little piece of it and put it on a sub, and then brought it over to ASM. And so here's an image that we got, and then we got a result from that. What I thought we were going to go, I'm going to, again, keep an eye on time. Let's actually figure this out. So right now, I have the sample over in the chamber, and we're going to zap it, and we'll see what we get. What is it? So chabazite can be a potassium emitter, a variety, it can be calcium, it can be sodium, or some combination of those, and we get something we call solid distillation, where we can get mixtures of specific cations that fit into specific sites. The X-ray didn't tell us necessarily which of those was. So bear with me. I'm laughing because there's another picture of my son from way back in the day. A little evil in his eye. All right, so I've connected to the scanner microscope, and I've put a sample in there that is this particular mineral. So this is a piece of that mineral at 30 times magnification. I can go up to 100. I can go 1,000, but we're going to lose any semblance of where we're at. But at 100, and then I can mess with this. Let me display this full screen so you can see it better. So there we have a couple of little, these crystals are a little white, by the way. And they have a very unique shape to them. And there's a little bit of surface dust on them. That's not perfect focus, but it's good enough to get an analysis. It's a unique shape. That tells us something. So if I go now to my other computer and pull this spectrometer, now I can scan the sample. So now different computers are actually running this. This is the one that runs the X-ray spectrometer. And if I go here, now I can get a spot and analyze it. So the one thing I'm not seeing much, I'm going to crank up the power a bit. If I can get back to that. I have to go back to the normal display. And then I'm gonna these things conductive, and so we'll coat them with carbon in a lot of cases. We can also use a gold palladium spark recorder too if we're not interested in chemistry. Oh, there we go. There it popped up. So I don't know if you can see this limited resolution here, but I don't know if you can see the elements that are present, but there's a little bit of magnesium, but aluminum, silica, a little bit of tiny bit of iron, and then potassium, calcium. So what that tells me is this zeolite is, the magnesium is a little unusual, but the calcium and potassium tell us it's a specific variety that actually has a mixture of these different cations in there. Can you see the labels on there? Okay. So yeah, this is how we use this, and often it's in concert. You know, we need different technologies to answer specific questions in this particular case. Geology was good enough for most people, but student wanted to see the technology, which I thought was impressive. I'm going to go back and see. Actually, I'm running out of time. Actually, I'm going to stop there just because the thin section that I had in there is not covered well enough in the charges significantly. So I'm going to open it up to questions here, and that's going to be where I stop. So thanks to Don, thanks to everybody. It's been interesting, kind of fun. That picture is from Upper River Extension Line. I actually got paid for some pictures last year. My colleagues wrote an article for Scientific American, and that was one of the ones that they actually used. It's a place called Woodhawk Creek. Beautiful, beautiful place. So, do we have any questions?
Some of the machines you have must work in a vacuum, and which ones routinely go up in space for the landings on asteroids and such?
Question is, do we use vacuum for these? And we do on two of those. Micro XRF has a vacuum. We don't have to turn on the vacuum for liquids, for example. The SEM uses high vacuum, and we can actually use variable pressure in that mode if we don't want to coat it, and that helps balance the charge. XRP doesn't use that. Diffraction would be difficult in space, but of course spectrometers are used extensively on different instruments, and usually different parts of the spectrum. You know, they could be X-ray spectra, could be gamma rays, could be visible light in certain cases. There's a lot of different spectrometers that are different cell dimensions of that particular mineral, and you kind of need specialized equipment in a lot of cases for that. We don't have that specialized equipment. Single crystal X-ray diffraction, for example, is one, would be an important piece of that information. But you have to do some really good science and really good measurements to be able to name a new mineral species, for example.
Interesting. Thank you.
One of the micrometeorites had a little metal bleb in it, and it was the first time I had seen iridium in a spectrum. And iridium, we know, is the iridium layer that is related to the Chicxulub crater. But there was also rhenium and osmium in that particular little metal bleb. Is it an alloy? Is it a new mineral? We don't know.
My Gym and Mineral Club has acquired a high school Geiger counter from 50 years ago. It's the size of a big shoebox, and it has a wand at the end of a 6-foot cord. So we're going to try and incorporate it into our next show. So it's easy to get a wind-up clock that has radon hands, okay? And it's easy to get uranium glass. Where would you get some good samples to show this off?
You could come ask me.
You got some?
I have a student actually that's going to be bringing in some monazite sand, which monazite has rare earth elements and radioactive components, thorium, uranium, things like that. Pardon?
We don't have thorium in any real amount on this continent.
It's in certain, there are thorite, there's a thorium oxide mineral, and it does get incorporated into things like monazite, and there's allanite is a epidote mineral that might have some of that. So there's a few. It also, they measured in zircons too. That's one of the elements, radioactive elements that they can measure that helps in the dating process for geochronology. But if you need samples, we have in the basement, we have this, it's in a box and it's really hot. And I forget if it's petrified wood or if it's dinosaur bone, but it's full of, it's either cancrinite or uraninite is what has replaced that particular specimen. And when you put a Geiger counter by it, stand back. So we have it in a storage area that's relatively safe. It was part of the collection that came long before I was there, and we have it.
There's two different kinds, one for the dinosaur bone and another for the radioactivity.
Well, when we collect in the Upper Missouri Breaks National Monument, for example, we have to have a permit to collect there. And we know the monument manager, and yeah, we go through proper channels to collect where we know we can collect. And there's very specific places we can't do that. The radioactivity, though, is just it's good lab practice to store it safely. And I would love to have that on display where we have it in leaded glass, and then you push a button and the Geiger counter goes off. That would be some work to do that properly, though. But you could get in touch sometime if I could probably share. I have geo standards, we call them, that have radioactivity in them, and I could probably share some of that with you. What mineral club, by the way?
Chippewa Valley Gym and Mineral Society.
Chippewa Valley.
So this is Wisconsin.
Yeah. I was thinking the St. Croix one. I know the retired chemistry professor from River Falls, David Rusterholz is his name. He runs the St. Croix Rock Hounding Club, I think, is what it's called, something like that. Yep. Sure. Yeah, we could talk.
Yes, I have a comment question type of thing. I understand there's samples from the Bennu asteroid that are absolutely remarkable results coming out. Did they use the kind of instrumentation that you have up here available for testing that?
And probably at much higher, and equipment like that. The people working on that stuff absolute top of their game. They have access to the absolute, best equipment, and they really know their stuff.
It's been amazing what they've been coming up with.
I haven't been following it other than, is that the one that landed in Utah? And
Yeah.
I've seen a little bit
that
of those
one.
story, but
Yeah, it's been coming out like right now,
Yeah.
all the information of the different things they've been finding it. Pre-amino acid stuff, yeah.
yeah. Not with this equipment. Yeah, not organics. We can see oxygen. We could see nitrogen, if it was there. We don't look for that, in a sense.
But it's an exciting time.
Absolutely.
Thank you.
Yeah, absolutely. Anything else? You can also, thank you. If you look up McAllister College and go to the geology department, you can find my email address. If you've got questions, you send them my way. I'm happy to try and answer them. But thank you.